So in the next part, we want to look into the recursive base filter and provide an introduction in how to derive the basic base filter framework for recursive state estimation. So again, recursive state estimation, what does that mean? State estimation, so without the word recursive, means that we want to estimate the state of the system. For example, where is a robot in the environment? Where is a certain object located? I want to estimate it, typically based on sensor information and also often based on control commands and things that change things. And recursive means here that we want to update our belief, where, for example, which state the system is currently in, based on new observations that come in, reusing the previous distribution that we had, and updating the distribution based on the new information. And this will turn into a recursive formula. Recursion is something that you probably know from your basic programming education, where you basically reuse your previous result and just update it based on the new information that is available. So again, what is state estimation? State estimation can be described by this probability distribution, and it says I want to estimate the state of the system X at time t, given all my control commands and my observations. So this is the state of my system at time t, for example, the position of the robot at a certain point in time. And we do this estimation given, so we have our observations, always referred to as Z, and my control commands for all the history, for all the past. So I started at one point in time, this was the first time step, and then I have them all up to time t. And I have this sequence of observations and this sequence of control commands, and I want to estimate where am I right now, for example. What's the state of the system? And that's what state estimation is about. And the recursive part of it comes into the game when I said, okay, I want to estimate P of xt. I want to change this posterior here so that we'll say P of xt given the rest is something where P of xt minus 1 pops up again. So that I can base my state estimation about what the state of the system at time t based on the belief I had about the system at time t minus 1. And of course, the estimate about t times, the estimate about the distribution up to t minus 1 then also only uses the observations and controls up to t minus 1. And then I kind of get new observation, get a new control, and I advance the belief that I had to the belief at the next point in time. We can start as an illustration with an example from the probabilistic robotics book of Sebastian Thun, Wolfgang Burgert, and Dieter Fox. It's a very prominent example that you've also seen in this course a few times. You basically have a robot that lives in a one-dimensional world, just has this x dimension. It has no idea where it is, and the only thing it can sense is actually a door. So if it stands in front of the door, its sensor will say door, and otherwise it will say no door, door, no door. That's the only thing that the system can do. So we will react to door events, basically. And so in the beginning, the system has no idea where it is, so it's basically a uniform distribution. So this is a belief. The belief of x is basically this distribution at before P of xt given the control commands and the observations. And now let's say it stands in front of the door and the sensor shouts door. Okay, where am I? If I have no idea where I am, I only know my sensor said door, and I have a map of the environment from which I know that there are 3 doors. They would say, oh, I'm either here or here or here. Right? Yeah, that's okay. That's a pretty good estimate. But it could also be the case that my sensor made a mistake, right? So it's still possible that I'm somewhere else, but it's of course more likely to be in front of a door. So what we can do is then we can use our observation, and the observation model will tell me, just based on the information that the sensor shouted door, I'm either here or here or here, or maybe somewhere else, but with a smaller probability. So I can basically update that belief into a new belief, which now encodes this information. I turn from the uniform distribution to this belief that incorporated one observation. And then the system basically moved through the environment. So after incorporating the sensor information, the robot drove, let's say, a meter forward, for example. And then we can see that the system moved forward, so the robot moved from here to here. But what we can also see is that then the probability distribution should move with it, right? Because if I was in front of a door, I need to shift this probability mass also a meter forward. I could shift it exactly a meter forward if I would perfectly know that the platform would exactly drive 1 meter forward. But often that's not the case. You know, you drive a meter forward and the system drives a meter and 5 centimeters forward. or it only drives 95 centimeters forward, or 99 centimeters, or 1.20 meters. You don't know. So there's some uncertainty in the motion, and this leads to the fact that this probability distribution kind of smears out. It gets wider, this distribution. So the peaks are not as peaked anymore, they get flatter and distribute probability mass over a larger area in state space, and therefore this distribution gets flatter. But then the system gets a new observation in. The robot again shouts door, or the sensor shouts against door, and again, if I don't know anything, where I have no prior knowledge, and just know that the sensor shouted door, I would have exactly the same distribution I had before, but now I need to combine this distribution with this distribution over here. And this leads to an effect where there's an overlap in the post between the two peaks. This will give me the highest peak, and I have a few other peaks here as well, and those other peaks basically mean I was right once, but wrong the second time, or the other way around. So as a result of this, we will have this distribution, and if we kind of move again further forward, we will have this distribution over here. And this is basically advancing the belief from one state to the next state using just the current sensor information and just the current motion control command is something which we refer to as recursive state estimation. And that's what we want to solve. We want to first solve it just in the form of a mathematical framework, so deriving the equations that tell us what do we need to do in order to estimate this recursive belief. So again, we start with this one. That's what we want to estimate. P of xt, so where are we right now, given all the observations from the past and the control commands from the past. So in this example before, these were the two motion commands and the two observations I had from that platform. And now I want to estimate where am I? Where am I, given that I have no idea where I was before. And that's where we're going to head to now. Okay, so we start by saying we're interested about the belief of the system, where it is at time t. And this is nothing else as the state estimation equation, or the definition of the probability distribution that is my belief. So where am I right now, given all the observations and all the control commands? So this is the definition of the belief. And what you see here, everything which is redly underlined is the part which has changed in this derivation. Okay, so the next thing we're going to do, we want to split up, or we want to modify this distribution here to simplify it for us. And one way to simplify it is to apply Bayes' rule. Yeah? Remember the thing that we did just a few minutes ago in the previous lecture on probability theory, we looked into Bayes' rule. So Bayes' rule allows me to swap certain elements in here between what's written in front of the given sign, what's written behind the given sign, given some background knowledge. So what we do now is, what we want to swap is zt and xt. So the variable zt, so the last observation, and the current state of the system, we just want to swap them, turn them around. That means z1 to t minus 1 and all the u's count as background knowledge. And so we apply Bayes' rule in order to swap those over here. So what we do is we kind of swap zt and xt. So xt and zt we are going to swap. So this is a normalization constant over here which encodes the evidence. So divided by the lower part of that equation that we defined in Bayes' rule, which is nothing else than a normalization constant. So I can just write it as a constant here. Okay, so what has happened over here? So in this first part of Bayes' rule, so this is the first part and the second part, here zt and xt have been swapped. Okay, so here we swapped those two. The rest stayed the same. And then we have the second part where everything is in there except the variable which is now here sitting in front. So everything else is in there, but not zt. So this is p of xt given z1 to t minus 1, u1 to t. So the plain vanilla application of Bayes' rule, nothing else has happened here. Okay, and now what I'm doing, I want to modify this part over here. What I'm doing is given I know where the system is right now, given the state of the world, given xt, so I know where I am, what's the probability of observing something, of saying, let's say I'm in front of the door? Also, given all the past observation, the past control commands. And here is something that we assume, we make an assumption which is called the Markov assumption. And the Markov assumption tells me, or says that given I know the state of the system, what happened in the past is decoupled from the future or independent of the future. So that means given I know the state, given I know where I am, all the past control commands, how I steered in the path, and the past observations, They don't tell me anything about what I'm going to observe right now or in the future. Okay? So this means all this part over here, this z1 to t minus 1, u1 to t, doesn't help me to estimate p of the likelihood of the observation. So I can ignore them, I can drop that, because there's an independence. This term and this term are conditionally independent given xt. That's what is said here. And this is what the Markov assumption does. So through the Markov assumption, this simplifies to p of zt given xt. So it basically says, what's the likelihood of an observation given I know the state of the world? And this comes in through the Markov assumption. The next thing we want to do is we want to modify this part of the equation here. So this is what we're going to change now. And what we're going to do here is we apply the law of total probability. So with the law of total probability, applying it, we can add a new variable. We can introduce a new variable to the system that we are integrating over. And we introduce the variable xt minus 1. Why are we going to do this? Because we want to end up getting a recursive equation. So an equation where we can move from xt to xt minus 1. Therefore, we introduce a new variable right now through the law of total probability that tells me where was the system at the previous point in time. So not where it is right now, where was it before? So we just add p of xt minus 1 in here after the given sign, and then times p of xt and integrate over p of xt minus 1. Okay, so this is what the result of the law of total probability looks like. So the expression gets a bit more complex, but there's no black magic behind it. It's just the plain vanilla application of the law of total probability. So I added this new variable xt minus 1. So it sits, this is the same distribution of what's written here. Just I added this xt minus 1. And then I have to also write the p of xt minus 1 given the previous background knowledge that I have and integrate over xt minus 1. So I'm integrating basically over all possible states where I've been before. So basically this thing is, where am I right now given all the old observations and all the motion commands? Basically it can boil down to, where am I right now given I know where I've been in the previous point in time, times how likely it is that I actually was there, and then integrating about all previous states. So I'm basically integrating over all possible previous states and estimate, given that I was there, how likely it is that I'm now in the state where I am or where I want to be, the p of xt. So we're adding this additional variable to kind of breaking down this chain of previous states and add just the most recent state to it through this law of total probability, but integrating over it so that we don't change the overall probability distribution. Okay, and then we're going to simplify this expression over here. So what's written here? It's p of xt, so probability where I am right now, given I know where I've been before, given all old observations which happened up to that time xt minus 1, and all the old control commands plus a new control command. So given I know where I've been in the past, in the previous time step, whatever I've seen before really doesn't matter anymore, right? It's again a Markov assumption. Whatever happened in the past, I don't care if I know where I am right now. The only thing which still matters is ut, because ut tells me how do I evolve from t minus 1 to t. So this is still valuable information. It's basically the last motion command that I've executed to the platform. But however I steered before is irrelevant if I know where I've been at the last point in time. So this equation simplifies to p of xt given xt minus 1 and ut. And all the observations and all the motion commands between the time step 1 and t minus 1 don't matter anymore. So we can eliminate them. So as a result of this, this simplifies to this expression over here, just using this Markov assumption. Basically, knowing where we've been in the previous point in time helps me to ignore everything which happened before. And then the last thing we need to optimize or to change is this expression over here. So what do we have here? We have the probability where I've been in the previous point in time, given all observations up to the previous point in time, and all control commands up to the previous point in time, plus ut, plus the last control command. So basically it's the same distribution that we started with here, except that we have one further motion command. So I know what I've steered, which motion I execute in the system. And what I'm doing right now, I'm making an independence assumption. I'm assuming it. Doesn't mean it's true. I just assume that the motion command I'm executing in the future doesn't help me to estimate where I am right now. Okay, so assuming I want to estimate where I am right now here in that position where I am, and I know that in the future I will go 20 centimeters forward, something like this. Does it help me to estimate where I am right now? You would say probably not, because what I'm executing in the future shouldn't help me to estimate where I am right now. If you think like this, it holds for most of the cases. You can, however, construct a situation where this is wrong. So if I would be standing in front of a wall, and you can assume that I have, let's say, a collision avoidance system running if I'm a robot, and I'm standing in front of the wall, it's very unlikely that I will actually bump into the wall. So if I'm here and I'm saying go 20 centimeters forward, I would bump into that wall. So it's unlikely that the system would have executed this motion command if I would stand so close to the wall. So there are certain situations where this independence assumption of ignoring UT does not hold. But in most of the cases, it's a reasonable assumption. So what I'm doing here, I'm simply ignoring the latest motion command that has been executed. I'm just ignoring it. Okay. I'm losing information here, but you can argue that quite often this information is not very useful, but there are corner cases where it could matter. But we are ignoring it, something that we assume independence. Not true. It's not a true independence. It's assumed independence. So if our model breaks, we're not good in state estimation. Revisiting the assumptions that we had made is a good idea, but our model makes this assumption now. And then we can look to this last term over here. P of xt minus 1 given z from 1 to t minus 1 and u from 1 to t minus 1. This is exactly the initial belief that I had, except that I replaced t minus 1 by t, or t to t minus 1. So, and this is now my recursion. So I reduced the estimate of where I am right now to the estimate where I've been before, plus some updates which only depend on the current control command and the current observation. So I can put in the belief, this is a belief xt minus 1 to make this recursion explicit over here. Okay, so it's just a replacement. It's nothing, there's no assumption, nothing in there. It's just the recursive term that I put in there. And that's basically the complete derivation of the recursive base filter. So we have started from here, from the belief at time t. We reduced it to the belief at time t minus 1, plus some update taking into account the most recent motion command and taking into account the most recent observation. And this is one of the key derivations, and a lot of state estimation techniques rely on this derivation. So if you think about the Kalman filter or the extended Kalman filter or unsalted Kalman filter or into a particle filter or a histogram filter or other recursive filtering technique that you know already or that you will get to know, they all rely on this mathematical framework. Okay? So it's the very basic derivation of the base filter from the beginning to the end. And it's clear also now which assumption we have made. So if we have applied base rule, that's not an assumption, everything good. We made a Markov assumption. That is an assumption that the past doesn't impact the future given I know the state in between. If I wouldn't know the state in between, there would clearly be a dependency. But given that I know the state of where the system is in right now, the past is independent from the future. And we have done this twice. Once for our first model over here, which will lead to something we call the observation model. And here, in there, something we call the motion model, the control model. And what we have used an independence assumption, assuming that a future motion command doesn't help me in the estimating the state of the past. And this was kind of the last step that we have done in here. These are the three assumptions that we have made when we have been deriving the general base filter framework. And these are the assumptions that the base filter does. But under these assumptions, there have been no simplifications in here. Of course, depending on the realization that you do for the base filter, so if you use Gaussian distributions to represent those probability distributions, then you start making assumptions or kind of make your model less general because you reduce everything to a Gaussian distribution, for example. But then you may be able to solve this very efficiently, and if your assumption is a Gaussian or close to a Gaussian, that's maybe a good idea to do. But so far, this was really the general derivation without making assumption about models we are using, or what kind of probability distributions we are taking into account here. Quite often in the literature, you find that the base filter is broken up into what's called a prediction step and a correction step. And so this is our final equation that we have. This part over here, the last part with the integral, is typically called the prediction step. And this second part over here is called the correction step. Why prediction and correction? Because what this part does, it takes the previous belief and advances the previous belief based on the control command. So based on, for example, which steering command I've executed, it estimates where it could be. It predicts where the system will be in the future. So it's a prediction step. And then we will get an observation in the new state, and this observation is used to correct potential mistakes that we have made in the prediction. So we take our observation into account in order to perform a correction of my prediction. And therefore, this is called the correction step. So if you have a bar over here, this is typically a notation for the predicted belief. The predicted belief is the belief where we only use the motion model to advance the state. And the correction step then multiplies this predicted belief with our observation model, and then this and a normalizer, and this then leads me to the corrected step, where I take into account that the sensor observation may tell me something different than the prediction step. And often we find in these base filter formulations an alternating prediction, correction, prediction, correction, prediction, correction step. And in every time step, I basically perform a prediction and a correction. Motion and observation, motion and observation. And I always advance the belief, estimating in which state the system is. And in the prediction step, we use something we so-called the motion model, which is P of xt given xt minus 1 and ut. And we have our correction step, which uses a so-called observation model, sometimes also called measurement model or sensor model, depending on the community you're in. I will most of the time use the word observation model in here, which is the likelihood of obtaining the observation that I got, given I know the state. So if I assume that I know in which state I am, how likely is actually to observe what I'm observing? And that's the question that we typically have to answer in this setup. And up to this point, this was the general derivation of the basic base filter. If you want to implement your base filter, you need to do certain things. Or what you need to do is you need to specify your motion model and your observation model. How do they actually look like? How does my belief look like? How do I represent this belief? Is this a Gaussian? Is this a sum of Gaussian? Is this an arbitrary probability distribution? This will have an impact on how those things look like. Also, how do I describe how I advance from time t minus 1 to t? Is this a linear model? Is this a nonlinear model? What do I know about the system? Is it a car that I know I have a steering wheel and a gas pedal that I can push? And this will constrain the motion how I'm going. I can't move sidewards with a car, for example. These are all constraints that I can take into account, need to integrate into my motion and my observation model in order to perform state estimation in an efficient manner. So the important thing to note in here is that there's a large number of different realizations of this base filter. So the base filter is just a framework for recursive state estimation, and there are different realizations which are out there. And they depend based on the assumptions that you make. Again, linear versus nonlinear models, for example, for describing the motion or for describing the observations. Can we assume Gaussian distributions, or do we want to represent arbitrary distributions? Do we need to be able to handle uniform distributions, for example, initially when we don't know in which state the system is in? That's something which it's tricky to do with a Gaussian distribution. Do we need to represent multiple modes, multiple hypotheses about the state? Do we want to represent the probability distribution in a parametric form or non-parametric form? These are all design decisions that I have to make, and they have an impact on how this filter actually looks like. There are different popular filters which are out there. Kalman filter and extended Kalman filters, they typically use Gaussian distributions for all our distributions, and a linear model for the Kalman filter, or linearized models for the extended Kalman filter, which basically performs a Taylor linearization, a Taylor approximation of the nonlinear function. And this is a very popular filter that you find very often in literature. Particle filters are an alternative representation, alternative realization of the base filter. They have the advantage that they allow for leaving the Gaussian world, so you don't assume that everything is Gaussian anymore. You can represent arbitrary probability distributions. This comes at a cost, at a computational cost, at a memory cost, but allows you to, for example, represent multimodal distributions in a very elegant way, but can handle basically arbitrary models, at least for the motion model, as long as we can sample from those models and can point-wise evaluate our observation models. Then we can use actually arbitrary models are not constrained to linear or close to linear models. Just to give you a very brief idea how such a motion model and observation model looks like, I just want to give you two very simplistic examples without going into the details, just to give you kind of visual understanding on how that could look like. Later in the course, we will explicitly look into observation models and into motion models. So for today, I just want to show you one short example, one instance how that could look like. So motion model is this part over here, was this part over here. So where am I right now? Given I know where I've been before and given I know which motion command has been executed. How does it look like? And we can represent it or illustrate this in this form over here. So what you see here is an illustration of a robot, so kind of a circular robot. It's looking over here at the point in time xt minus 1, and next point in time it's looking over here, so the system has actually been driving around over here, or assumed to have been driven over here. That's what the motion command tells the system. And the question is, where am I right now? Where am I actually? And then it turns out I get this probability distribution, this grayer. So the darker the values, the higher the probability. We can see this as an experiment. Let's say I put the robot in a certain state and I execute the same motion command, let's say 300 times. Then I get these 300 different dots of where the system actually ends up. And so these are the outcomes. You can see the outcomes of experiments, and they represent the probability distribution or an approximation of the probability distribution where I am after executing this command, knowing where I've been before. And these are different parameters for those models. For example, in this case, the system has a very high uncertainty in the angular movement, but can very precisely estimate how far it has traveled. So in this case, the uncertainty in this direction is very small, but is very large in the angular component. Here is the other way around. I have a higher uncertainty along the forward motion direction, but I have a smaller uncertainty with respect to the angular components. You can basically see this based on this kind of idea of experiments, of repeating an experiment and seeing where the system ends up. And this is something which we typically call a banana-shaped distribution. So it's kind of this, because the shape of a banana, which describes the motion. And this is a traditional so-called odometry-based motion model, where you count the revolution of the wheels of your platform and see where are you going to end up. And this is an example how this model looks like. So how P of xt given xt minus 1 and ut actually looks like. These are just illustrations of this fact. For the observation model, we can do something different. Again, a very small, simple example, as simple as possible, just to give you a visual idea on how that could look like. So consider we have a sensor. Let's take my laser pointer over here that you see here, and consider this is a measurement device. So it measures the distance to the closest obstacle. So whatever somewhere over here, you see the laser pointer. This is the it measures this distance. Just assuming this. So it says whatever, 40 centimeters, 35 centimeters, 50 centimeters. But this measurement is affected by noise. It's not perfect. Maybe it's 50 centimeters, but in reality, or then the system says it's 48 centimeters, or in reality it's 60 centimeters away and the system tells it's 62 centimeters away. So how often does it happen that I'm off, and how far am I off? And this is something which I can, for example, represent with a Gaussian distribution, representing Gaussian measurement noise, which is actually a not too bad approximation, if at least we're in the outlier-free case. So if you have a range sensor, the robot sits here and here is an obstacle, what's the probability of range measurement that I get? And maybe I assume this is a Gaussian distribution. So it's very unlikely to measure a meter if my object is 50 centimeters away. And it's also very unlikely to measure 10 centimeters if the object is 50 centimeters away. So 50 centimeters is very likely to measure, and 49 is also quite possible, 51 as well. But the further I move away from the actual distance, the smaller the probability gets. And this is an example for a simple observation model for range sensor with Gaussian noise of a single ray range reading in this most simple case. Just to give you an idea how such a model could look like. So by using such a motion model and such an observation model, I can actually estimate positions where a system is in the world and perform localization tasks. And that's something that we will gradually work towards in this course. First, we'll look into maps, and we'll look into how to describe motion, and then go deeper into those models until we reach that point in time where we can actually localize the platform. But this is kind of the guideline where we actually will move to. Which also brings me to the end of the lecture today. So we have seen the first part that probabilities are important in order to estimate a lot of state estimation problems, and they're a key tool that we are going to use. We have derived the base filter framework, which is a technique for recursive state estimation and allows me to estimate probability distributions taking into account the previous belief that I had, plus the new observations and the new control commands. And there are different ways how we can realize the base filter. So base filter was a general framework, and then there are concrete realizations such as the extended Kalman filter or the particle filter. And we will dive into the details of these filtering techniques in the future here in this course. If you implement such a base filter, you need to specify what kind of distributions are you looking into, what kind of models do you have. You have to specify your observation model and your motion model as the central models in the base filter, which you need to specify, as well as how the probability distributions look like. So that's important if you want to actually implement it and build such a filter as a concrete instantiation of this general framework that we have presented over here. So if you want to dive a bit more into that and want to read a bit more about it, I can recommend the Probabilistic Robotics book. Chapter 2.1 and 2.2 basically is a repetition of this probability primer that I have talked about, and the chapter 2.3 is an introduction to the base filter using a similar notation that I have used here. So it should be actually straightforward if you want to dive more into the detail and read again what I have presented over here. So that's it from my side for today. Thank you very much for your attention, and I hope you enjoyed this starting part into the course and get an idea on how state estimation at least works on a general, as a general concept, and we will make that more concrete in the near future. Thank you very much for your attention.